Hi everyone. Let's start chapter 10 by talking about trig identities. Now, first of all, the word identity in a math class is basically any equation that is always true, no matter what. And when we're talking about trig identities, it's basically an identity that has one of the trig functions in it. So these are equations involving any of the 6 trig functions that are always true. Now, a lot of them we've learned already. We're just going to kind of put a name to it and summarize and organize them. We call these our fundamental identities. And remember, the word fundamental means simple but important. So let's start with the reciprocal identities. Each trig function has a reciprocal. That's why there are 6 trig functions, but we can have 2 groups of 3. So what we usually say in words is sine and cosecant are reciprocals. Well, to be an identity, we have to turn that into an equation, and this is how you would write that. You would say sine x equals, and then the reciprocal would be 1 over. So you would say 1 over cosecant x. Then we have cosine and secant. So you could say cosine x equals 1 over secant x. And then our third reciprocal pair was tangent and cotangent. So we could say tangent x equals 1 over cotangent x. But reciprocals work backwards too. So I'm going to kind of create another 3 here. First, we have cosecant x equals 1 over sine x. That's kind of the same as number 1. I just flipped the trig functions. But remember, reciprocals work either way. So in words, if I say sine and cosecant are reciprocals, that means each one equals 1 over the other one. Then we have the same relationship with secant and cosine, and cotangent and tangent. All right, our next set of identities is the quotient identities. The first one is a very fundamental one we use all the time. We say tangent x is sine x over cosine x. But we also have one for cotangent. This one we don't use quite as often, but we definitely want to know this one too. It's basically taking tangent, being sine over cosine, and then going back to our reciprocals and saying, well, if tangent and cotangent are reciprocals, then I can just take that sine over cosine and flip it and get cosine over sine. So that's why cotangent ends up equaling cosine over sine. Okay, a third set of identities that we already learned in chapter 9 was the cofunction identities. There's a whole video on this, so I'll just go quickly and remind you. These are for the ones where you have either 90 minus x, or in radians, pi over 2 minus x. And basically it comes down to taking the co in front of the name and either adding it or taking it off. So you can turn a sine into a cosine by using cofunctions, by using the pi over 2 minus x. We also have secant and cosecant, and tangent and cotangent. So, again, there's a whole video on this. You can go back and watch the cofunctions video if you want to refresh on it. Just don't get them confused with the reciprocals. The only one that's the same for both are tangent and cotangent. Tangent and cotangent always go together. If you're talking reciprocals, sine goes with cosecant, and cosine goes with secant. If you're talking cofunctions, sine, cosine, secant, cosecant. It's just the word co in front of the same name. And then just like we did with the first set of identities, they work the other way too. So we'll make it a set of 6 again. Cosine and sine, cosecant and secant, cotangent and tangent. And basically the way I described it in our earlier video, I said if you want to turn a pi over 2 minus x into an x, either add a co in front of the name of the function if it's not there, or if it is there, take it off, get rid of it. Our next set of fundamental identities is the Pythagorean identities. And we haven't done these together yet this year, but you probably have seen them before, maybe in a math class before or something. If not, that's okay, we'll go over them right now. What I want to mention about the Pythagorean identities is that a lot of times in a textbook, they'll tell you there are 3 different Pythagorean identities. There is what I consider the main one, which is sine squared x plus cosine squared x equals 1. And I showed you where that came from on a different video, on the one called Deriving the Unit Circle. If you want to see, go back and watch that video. But basically, that's the main Pythagorean identity. Now, like I said, a lot of textbooks will tell you the other Pythagorean identities are 1 plus cotangent squared x equals cosecant squared x, and tangent squared x plus 1 equals secant squared x. And what I want you to realize is it's not really 3 different equations. What it is 3 versions of one equation. And I want to show you what I mean by that. So let me start with the main Pythagorean identity. We have sine squared x plus cosine squared x equals 1. And that's the one I definitely want you to know. And I'll show you why. If you know that one, you kind of automatically know the rest of them. So let's say I took this equation and I divided both sides by sine squared x, which I'm allowed to do. It's an equation. Or basically what I'll do to simplify it is I'll just divide each piece separately by sine squared x and simplify each part. Now the first part is just 1. Anytime you have anything over itself in a fraction, it cancels and just leaves a 1. Sine squared x over sine squared x is 1. Now for the middle part, you have, if you kind of ignore the squared for now, you have cosine x over sine x. That was one of our reciprocal identities. That's cotangent x. Now if they're both squared, you can still do it. It just leaves squared. So cosine squared x over sine squared x is cotangent squared x. Now, for our last part, again, if you kind of ignore the squared for now, 1 over sine x, that's one of our reciprocal identities, that's cosecant x. So 1 over sine squared x would be cosecant squared x. And that's what I said textbooks call that the second Pythagorean identity. It's not. It's just a different version of the first one. Now let's do the same thing. Let me start with the original. Sine squared x plus cosine squared x equals 1. This time, let's divide everything by cosine squared x. And I think you guys are probably guessing now we're going to end up with that third equation. So for the first piece, sine over cosine is tangent. That means sine squared over cosine squared is tangent squared x. The middle piece this time is the 1, because cosine squared x over cosine squared x cancels. And the last piece, 1 over cosine x would be secant x. So 1 over cosine squared x, secant squared x. See, those are the two other Pythagorean identities. But like I said, as long as you remember the main one, as long as you guys know this one right here, sine squared x plus cosine squared x equals 1, if you're taking a test and you kind of get confused, let's say you forget, you're like, well, was it secant squared plus 1 equals tangent squared, or 1 plus tangent squared equals cosecant, you get kind of confused on those. You just find a little piece of scratch paper, you write down the one you know, sine squared x plus cosine squared x equals 1. You do the quick work we did right here, divide it by either sine squared x or cosine squared x, and then you see, oh yeah, it was 1 plus cotangent squared x equals cosecant squared x. Or oh yeah, it was tangent squared x plus 1 equals secant squared x. And you can very quickly create the other two from the first. But it is important that you remember the first one, the main one, sine squared x plus cosine squared x equals 1. Now before we move on, I want to show you another real useful thing you can do with the main one. So let me write it down one more time. Sine squared x plus cosine squared x equals 1, or actually I'm going to do this twice, so let me write it down 2 more times. But this time what I'm going to do is, I'm just going to kind of move things around, because you're allowed to do that too. This is an equation. And when I say move things around, I say let's start by, I'm going to subtract cosine squared x from both sides. And cancel that cosine squared x out. Now what you end up is sine squared x equals 1 minus cosine squared x. Now, we don't really consider that one of the versions of the Pythagorean identity, but it's very important because that's your relationship between sine and cosine. If you ever want to turn sines into cosines or vice versa, that's how you do it. And then let me real quickly do the other one. This time we'll subtract sine squared x from both sides. Cancel the sine squared x, and we get cosine squared x equals 1 minus sine squared x. So basically a good way to think of this is when you're dealing with sines and cosines, as long as you're dealing with squared terms, and that's important, I'm actually going to add it on here. All Pythagorean identities are for squared terms only. But as long as you're dealing with like a sine squared x or a cosine squared theta or something like that, if you're ever thinking, well, I have sines in this problem, but I would rather have cosines, that's how you make the switch. You can change a sine squared into a 1 minus cosine squared of anything, x or theta, and you can change a cosine squared into a 1 minus sine squared. But it is for sine squared or for squared terms only. So don't think like sine x equals 1 minus cosine x. That would be a mistake, and that's wrong. So now that we've reviewed our identities, our main goal for today is going to be simplifying identities, or simplifying expressions, really. So every identity that we've learned so far that we just summarized in the video can be used to do substitutions. But I want you to realize, let's take a look at this example right here. We have tangent x equals sine x over cosine x. That's one of our fundamental, basic, simple identities. We call it a reciprocal identity. And what I want you to realize is that that's actually two different substitutions. Sometimes you might want to take a tangent and change it into sine over cosine. Sometimes you might want to take a sine over cosine and change it into tangent. So those are the two substitutions you can do. I said, number one, I can take a tangent x in a problem and rewrite it as sine x over cosine x. Or I could do that backwards. If I have sine x over cosine x in a problem, I can change it to tangent x. And that's for every single one of our identities. Every equation works forwards and backwards and can be two different substitutions. So the goal for today, I'm going to give you some probably messy looking trig expressions, kind of big with a lot of different functions in them. And the goal is to simplify them as much as possible, try to make them smaller, cleaner. So here will be our first example for today. We have tangent x times cosecant x, and I said just simplify it. It's already pretty simple. There's only two trig functions in this, so hopefully there's a way I can maybe combine it, cancel something out, and turn it all into one trig function. That would be the only thing that's more simple than what we're already looking at. So let's think about some things we could do. Number one, I could take that tangent x and I could use a reciprocal identity and write it as sine x over cosine x. And then I say, well, I have a cosecant x. Maybe I'll use my, my reciprocal identity. And I'll write the cosecant x as 1 over sine x. And that was the trick. See, now you can see I'm multiplying fractions. The first one has a sine x on top. The second one has a sine x on bottom. Those cancel. And what I end up with is basically just 1 on top and cosine x on bottom. And I say, I'm going to go one step further. If I want to make this as simple as possible, I'm going to use a reciprocal identity again. I'm going to say 1 over cosine x is secant x. And that's my answer. So that's how we do simplifying. Like the first step was unsimplifying. You know, I took my nice small little tangent x times cosecant x and I turned it into a fraction problem. And it looked like I was unsimplifying. But after the sine x's cancel, it did clean up nicely and it turned into just secant x. Now here's another one. This one is a little bit more complicated. We have cosine x times secant x minus cosine x in parentheses, and the whole thing is over sine x. Now you have some choices here, the way you're going to approach this. I would probably use a distributive property first and get rid of those parentheses. So I'm going to distribute the cosine x. I'm going to have cosine x times secant x minus, and then cosine x times cosine x is cosine squared x. Remember, anytime you multiply a trig function by itself, you're basically getting something squared, and we use that notation where the squared comes after the name of the trig function. And the whole thing is over sine x. So let's focus on this part right here. Cosine x times secant x. I'm going to do the work off to the side to show you where it comes from, but there's actually a nice neat shortcut to this. The work to simplifying this would be to say, well, if I'm doing cosine x times secant x, I'm going to leave the cosine x, and I'm going to say, well, a secant x is 1 over cosine x. And then see, this cosine x cancels with the one we're dividing by, and you just get a 1. So cosine x times secant x is 1. Now the shortcut is, those are reciprocals. Multiplying by reciprocals always equals 1. Like 2 times 1/2 is 1. 10 times 1/10 is 1. It works with trig functions too, so you can just remember that. If I ever do like tangent x times cotangent x, that's just a 1. Or this one, cosine x times secant x, that's a 1. Or the other one would be sine and cosecant. Anytime you multiply by a reciprocal, you get 1. So what I have is 1 minus cosine squared x over sine x. And now, as soon as I see that cosine squared x, I immediately think of Pythagorean identities. Now, that doesn't mean it's always the right thing to do. Doesn't mean every time you see something squared, you have to do a Pythagorean identity, but it's a very good tool for you to consider. And in fact, this is that last one we talked about. If I have 1 minus cosine squared x, that's like having a sine squared x. And remember, that's kind of our shortcut for changing sines to cosines. If you ever have 1 minus one of them squared, you can turn it into the other one squared. And now this is going to clean up really nicely because I have basically a sine squared on top and a sine on bottom. One of them is going to cancel. I can cancel one of these sines on top with that one on bottom. And for my final answer here, I just get sine x. That's it. Just a nice, simple, easy sine x. So that whole big messy, if you look at the original problem in white, cosine x times secant x minus cosine x all over sine x, it all simplified to just a nice, simple sine x. And that's what we're doing right now. We're just practicing using identities to simplify expressions. Now, when you're doing that, sometimes it can help to factor. So I want to talk about factoring with trig functions. There's a couple ways to do factoring, and the first one, and probably the easier one, is factoring out common terms. So let me show you an example where we might do that. I'm going to say factor and simplify this. And as soon as I look at this question, I notice I have a sine x right here and a sine x right here. That's a common term that you can factor out. And factoring out means like reverse distributive properties, when you divide it and bring it out front. So I'm going to kind of think of this like it's in parentheses. I'm going to divide or factor the sine x out and then see what's left over. So on the first part, I had a sine x. I divided by sine x. That leaves a 1. Then minus. On the second part, I factored that sine x out. It's gone, and it just leaves the cosine squared x. So that was the factoring part out. I did reverse distributive property. I divided that sine x out and brought it out front. Now what I have inside the parentheses is the same substitution we did on the last example. I'm going to say that 1 minus cosine squared x, I can change that to a sine squared x. And then for my final answer here, if I have a sine x times a sine squared x, that would be sine cubed x. Exponents work the same way they do with numbers or variables. If I have one of something and I multiply by 2 more of them, I have 3 of them. That's the third power cubed. So if you have a sine squared x and you multiply it by another sine x, you get sine cubed x. And that would be my final answer for this one. That's my simplified answer. Now, the other part of this that's a little trickier, the other type of factoring, is the other type of factoring. So I said, you can also factor it just like a quadratic, as long as you have more than one of the same trig function. And let me show you what I mean by that. Let me start with no trig functions, just ordinary factoring. So let's say I had x squared plus 5x minus 14. And I asked you to factor that. You would factor it like this. You'd say, well, I have 2 factors. They're both going to start with x. I'm looking for numbers that multiply to negative 14 and add to positive 5. That would be a positive 7 and a negative 2. So that factors into x plus 7 times x minus 2. Now, let's say I gave you the exact same problem, but instead of each x, I had a trig function in there. Like maybe it was tangent squared x plus 5 tangent x minus 14. So you can see I have the exact same number pattern. I have something squared plus 5 times something to the first power, the same thing to the first power, minus 14. Now you could factor this the exact same way, but the difference is, see over here, you have x's, and that's what goes in your factor. Here you have tangent x, so that's what goes in that factor. Each factor is going to start with not x, but tangent x. And then you do the question the same way. You're looking for numbers that multiply to negative 14 and add to 5. So it would be a plus 7 and a minus 2. So you can see you can factor trig, and notice up here I said you have more than one of the same trig function. So you're going to have the same trig function, one of them just ordinary, one of them squared. And then in that problem, that's it. You're not going to have like a tangent squared x here and a sine x over here. You can't factor that. Or if they're mismatched, any two that don't match. But if they do match, you can do the factoring, and whatever that trig function was is the one that ends up starting each of your factors. And you can see, having these two right here side by side, you can see the relationship between factoring with x's and factoring with trig functions. So keeping that in mind, this will be our last example for today. We're going to factor cosine squared x minus 3 cosine x plus 2. So the first thing I notice here is exactly that pattern we just talked about. I have the same trig function twice, cosine x. One of them is squared, one of them is not. One of them is a regular cosine x. That makes this that quadratic pattern. So if I can find the numbers that work, then I can factor this, and my factors will begin with cosine x. Now, once you've realized that part, the rest of it is finding two numbers that multiply to positive 2 and add to negative 3. That would be negative 2 and negative 1. Negative 2 times negative 1 is positive 2. Negative 2 plus negative 1 is negative 3. So I put a negative 2 on one of these, a negative 1 on the other, and I'm done. I factor. So yeah, you can factor it as long as the question is set up like a perfect way. Same trig function twice, one of them regular, one of them squared. You get that pattern for factoring, and you can do it just like any other quadratic.